Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss concept of entropy and physical significance of entropy. Let's begin. What is entropy? It is a thermodynamic variable which is a function of the state of the system, and that is called the entropy. Entropy basically known as the degree of disorderliness of that of particular thermodynamic system. It has different values at the initial state and final state of that of thermodynamic process. Means at initial state the value differs to the final state of that of particular thermodynamic process. Again, as it is a measurable property of that of system, it describes the ability of the system to do work, means that describe the disorderliness of that of particular system. Again, entropy is very useful in the system study of the behavior of that of heat engine. Throughout the concept of entropy, we can study a very good ideas, a lot more ideas regarding heat engine. Now, mathematically we have to show what is the entropy is. Let we draw a PV diagram. Let we consider pressure here, pressure in y axis and volume in x axis. Here is the volume V in x direction and pressure P in y direction. Let us consider three isothermals I1, I2, I3. These are the three isothermals I1, I2, I3. Since the processes are isothermal, means in that of particular process temperature treated as constant. So I1 at temperature T1, I2 at temperature T2 and I3 at temperature T3. Let A1 and A2 are the two adiabatics. Let us consider two adiabatics, one is A1, another one is A2, which intersecting that isothermals, two adiabatics, A1 and A2, where heat radius constant. These are the isothermals I1, I2, I3. These are the adiabatics. A1 and A2. These two adiabatics intersects the isothermals at the points like A, B, C, D, E, F. A, B, C, D, E, F. Let consider the Carnot cycle A, B, C, D. Here the heat flow rate we consider Q1, here is the Q2 and Q3. At that Carnot cycle, the direction will be this. So here let me consider Carnot cycle. This Carnot cycle A, B, C, D, A, B, C, D. In this case, what happened? In this case, during isothermal process, AB, what happened here? The working substance absorbs Q1 amount of heat from that of source. The working substance absorbs Q1 amount of heat from the source at temperature T1. At temperature T1. So the increase in entropy of that of system, therefore increase in entropy of the system, that is heat divided by temperature Q1 by T1. Next, during that isothermal process, one is isothermal expansion and another one is isothermal compression. This is the isothermal expansion, means the increase in entropy of that system, but where it is the isothermal compression in that of a particular Carnot cycle. So during that of isothermal compression, the working substance rejects the Q2 amount of heat to that of sink at temperature T2. So we write here, during isothermal compression the working substance rejects Q2 amount of heat to the sink at temperature T2. Therefore, what happened here? That is the decrease in entropy. So the decrease in entropy of the system is equal to Q2 divided by T2, that is the decrease in entropy. Here the increase in entropy in case of isothermal expansion, that is the decrease in entropy in case of isothermal compression during that of ABCD Carnot cycle. Again, what happened in case of adiabatic process? Again, there will be two types of adiabatic process. One is adiabatic expansion and another one is adiabatic compression. So during adiabatic process, adiabatic process BC and DA. This is the adiabatic curve, that is BC and DA, BC, DA. So during adiabatic process BC and DA, entropy remains unchanged. Entropy remains unchanged. Why? Since heat will be constant here, so entropy remains unchanged. So from Carnot's heat engine concept, we say that is Q1 by T1 is same as that of Q2 by T2. So from theory of Carnot's heat engine, from theory of Carnot's heat engine, that is Q1 by T1 is same as Q2 by T2. So similarly, we take D, C, E, F Carnot cycle here. What happened here? That is heat Q2 is absorbed at temperature T2 and Q3 amount of heat is rejected at temperature T3 in that of particular Carnot cycle DC, EF. So we write here let I choose that one as equation number 1, comparing this to 1. So during similarly for Carnot cycle D, C, E, F, when amount of heat Q2 is absorbed at temperature T2 and amount of heat Q3 is rejected at temperature T3. So according to that of Carnot's heat engine concept, Q2 by T2 is same as Q3 by T3. Let equation number 2 here. So from equation 1, that is Q1 by T1 is same as Q2 by T2. So here Q2 by T2 is same as Q3 by T3. So overall we can say from 1 and 2, from equation 1 and 2 we have, that is Q1 by T1 is same as Q2 by T2 is same as Q3 by T3. Means generally we can say that is Q by T, heat to that of temperature, is always a constant. Okay. So the ratio of, this is the ratio, is called the change in entropy between the two states of that of system. This is the ratio, is called the change in entropy the change in entropy between two states of the system. Two states of the system. We consider a system, it has the states like initial state and final state. That ratio indicates the change in entropy. So, let me consider S1 and S2. Let me consider S1 and S2 are two entropy of the system. Two entropy of two states of the system are the entropy, not two entropy. Two entropy S1 and S2 are entropy, are the entropy of two states of the system. So, the change in entropy is similar at that of ratio. So, S1, therefore, S1 minus S2, that is Q by T, that is the ratio is called the change in entropy. Change in entropy between the two states of the system. So, let we take the entropy of two states of the system is S1 and S2. So, the change in entropy, that is S1 minus S2, is same as that of ratio Q by T, that is denoted as del S is equal to Q by T. If that are two states, we consider the two states here. Let we take the two states are very close to each other. What happened here? If two states, as we considered, are very close to each other, and dq is the very small amount of heat. Dq is the amount of heat absorbed, or rejected. That is the change in it, amount of heat absorbed or rejected in going from one state to another. Going from one state to another state. So, that equation changes to, therefore, we can say it will be changed to ds is equal to dq divided by t. So, in general, we integrate it. In general, the ds from the state S1 to S2 and that dq by t integration from initial state to final state. From initial state to final state. That is the basics of entropy. That entropy remains constant in a reversible process, but increases in an irreversible process. But here we take the reversible process as Carnot's heat engine cycle, so the entropy will be constant. So, I write 2 points here. Entropy is constant for reversible process. Similarly, it increases in irreversible process. Okay, it is constant for reversible process reversible process it is constant, and it is increases in case of irreversible process. This is constant and increases. Okay, this is all about the concept of entropy. Now what should be the physical significance of that of entropy? Physical significance, it has so many physical significances. So entropy S of a system is the physical property like internal energy, temperature, which can be measured in the laboratory. Like that kind of physical property, entropy is same for a particular thermodynamic system, and it provides an alternative statement of second law of thermodynamics. Means we states that only those processes are possible for a system in which entropy of the system plus surroundings always increases. Only those processes are possible for a particular system in which entropy of the system plus its surrounding, entropy of that of system plus its surroundings always increases. So that type of thermodynamic processes are taken into consideration, or this type of thermodynamic processes are possible. So by using that segment towards the second law of thermodynamics, how entropy helps to describe it. So according to this statement, only those processes are possible in which entropy increases, means those processes in which entropy increases, that type of processes are allowed, or that type of processes are possible. Some examples, let I prefer some examples in which that principle holds good. The examples like heat can flow from higher temperature to lower temperature, and again free expansion of a gas is possible. Again free expansion of a gas is possible. In these two cases, 1 and I, we see here the entropy is increases. That is why these two processes are possible. But here the processes causing decrease in entropy are not possible. Some examples in which the entropy decreases and that type of processes are not allowed or are not possible. Some examples like, similarly the heat can flow from higher temperature to lower temperature, but not flow from lower temperature to higher temperature. So heat cannot flow here, heat cannot flow from lower temperature to higher temperature, and free compression of the gas is not possible. In expansion entropy increases, but in compression entropy decreases, but that type of thermodynamic processes is not possible. So free compression of a gas is not possible. So with the help of this video lecture, we understand what is the concept of entropy. Mathematically we formulate the entropy taking an example of Carnot cycles. Finally we take the relation, the mathematical form of that entropy. Means entropy is constant for reversible process and it is always increases in case of irreversible process. These two are the mathematical way to describe that entropy. And finally physical significance of entropy. These are the physical significances of entropy. So with this useful and informative notes, let me wind up this session. Thank you.